Okay, it just turned 5. Okay. Okay. Welcome to the initial Calumet Revisited Forum of the new year. I am Michael Bowes of the Association for the Wolf Lake Initiative. I am co-host with Dr. Valerie Penninan of the Calumet College of St. Joseph. Calumet Revisited is funded in part by the Indiana Humanities and the National Endowment for the Humanities. Before we hear from tonight's speaker, are there any announcements? If not, I have two. Ollie's Winter Wonderland at Wolf Lake Festival is on Saturday, January 14th. It includes a walk at Eggers Grove at 1 p.m. It's tree identification walk. And then in the morning at 10 a.m., there'll be a Zoom meeting on watershed memories. Also, the Calumet Nature Exchange meets via Zoom at 7 p.m. Tuesday, January 17th. And remember, licensed teachers in Indiana and Illinois can earn an hour of professional development credit by participating. The presentation this evening is being recorded. The recording will be available within a week on Ollie's website. Would everyone please remain on mute? After the presentation, we will have a question and answer session. Tonight, we will hear from Dave Dolak, who will be talking about rocks on the beach. There will be a question and answer session following his presentation. I think I've repeated that. Dave?
Okay. Well, thank you, Michael. My name is Dave Dolak. I've spoken in front of all of you before. I'm a member, was on the board for a couple years. I'm a professor of instruction in the science and math department at Columbia College, Chicago. I'm an environmental scientist, geologist by trade. I worked at Argonne National Laboratory for a number of years. I did my graduate work at the Indiana Dunes National Lakeshore Park in the 1980s. And so I've been doing this talk here and leading tours of the beaches in the national park here now for a couple of years. So I developed this talk to sort of, a lot of people beachcomb, and we have a very interesting beach from not just the dunes, but anywhere along the southern shore of the lake. And so this talk is going to be about how you can read the geology of sort of the Great Lakes by the rocks that you'll find on the beach here on our south side of Lake Michigan. So I will start out. I'm going to try to give a sort of a geologic perspective of what you look for, why you look for it, what that tells you. So I'm hoping everyone can see my screen, and I'm going to minimize me so I can see my screen fully. So if there's any problems, I'm not going to be looking at chat. So while this is going on, so okay. So does at least Mike's on. Mike also has his speaker on. So Mike, can you see that I've moved my screen? Is that good?
Yes.
Okay. All right. Very good. And I don't know why that's not working. So, all right. Well, at any rate. Okay. So I'm going to give a little story. Geology is a sort of a science about, it's a story science in an area, in a sense. I'll talk about our study area, the kind of rocks that we find, why we find them there, which is based on a sort of ice age things here. Then we'll go to some specific rocks and talk about the time periods these are from, and then fossils also that we will see. So, okay. I teach at the Arts and Media School. And so I really like to think of geology as sort of an artistic way of looking at things as far as sciences, because it really is a story, because geology talks about a sequence of events from billions of years ago, which the new term everyone talks is, of course, deep time, through today. And so that means there's been a lot of change. There's changing scenes, there's changing locations, as we're going to see because of plate tectonics movement, changing environments, characters change, especially plant and animal communities based on those first 2 points above. And I'm going to try to acquaint you a little bit with the, the language that a geologist might use to describe some of these things. All right, so, everywhere we are is geology. Everybody, I think too often in our area, people think you got to go like to the mountain or the Grand Canyon or something to see geology. But everywhere you are has geology. This is, of course, probably the most obvious example of our geology. The dunes.
That's why he didn't hear it.
What
I love the Grand Canyon, but we don't need it today. All right. So take a walk along the beach. State Park, National Park, Whiting Beach, Walhalla, anywhere in the area. And you will see, depending on what the waves have brought in, it's really pretty funny sometimes. You can go one day and be a lot of rocks washed in, and then the waves come in and they're gone. They haven't really went anywhere. It's just sand has buried them. But I think most of us have been along the beach and we sort of know that interface between the where the waves are breaking and the higher up sand areas is sort of where you can find rocks and they're sorted by size. So we're going to sort of talk about that as well. In the dry time, it sort of looks like the picture on the left, and when they're wet, things sort of glisten much more nicely. So rock basics. Rocks are solid substances made up of minerals, combinations of minerals. There's my joke. That's my joke. I'm a guitar player, people know, so there I go. There are 3 basic types of rocks. There are igneous rocks, and they are directly cooled from being molten. They could be cooled below the surface, something we call magma, or if that magma comes to the surface, we sort of term that as lava. And that affects the rate of cooling. If they cool below the surface, they cool more slowly. You tend to have larger crystals formed. If they cool above the surface, the crystals are very small. The crystals interlock because these were sort of you almost think of ice crystals sort of melding together. Sedimentary rocks are rocks that are assembled from other rocks. So as erosion breaks down either of the other 2 groups of rocks or sedimentary themselves, and then they get re-solidified or re-lithified as the particles get glued back together or pressed back together, or in certain chemical kinds of rocks, the minerals precipitate out of water. But these are the general group called sedimentary. These rocks often exhibit layers because they were laid down in a sequence. Igneous rocks can do that, but it's not quite as common. And then metamorphic rocks are rocks that have been changed by heat or pressure, and they were either one of the other 2 rock types. So you can have some igneous rocks that, let's say, they get caught up later in mountain building activities, and then the tremendous forces to twist the mountains above the surface or etc. It will actually reform the minerals and the crystals in the rocks, and you get a different type of rock. You get metamorphic, or same with sedimentary. You can have rocks pushed further back into the earth where they partially remelt, not completely, but then they have sort of reformed. So that's what metamorphic rocks are. And characteristic of metamorphics, they may exhibit something called banding. It looks like it's a layering, but it's not really layers, because layers imply a sequence of events, like the mess on my dining room floor at the moment. I've got layers of papers there because the older ones I've thrown down first. But banding means the crystals are sort of aligned into bands, and that is characteristic of they've been involved in heat and or pressure conditions. So igneous rocks, or here's sort of the 2 types of igneous. If it comes to the surface as lava, we call that extrusive. They cool quickly with small crystals. And if igneous rocks come up from, deeper in the earth where they're fully molten and they cool slowly below the surface, they're called intrusive. The crystals are larger, etc. Again, metamorphic rocks are going to be where you've had conditions such as 2 plates banging together, where you might with the tremendous force, you could actually fold rock layers, and that's what pushes up mountains. And so that actually can change the composition of the crystals, and you will make metamorphic rocks. You can have, where my arrow is pointing here, you can have rocks that if they're close to the molten magma, the heat of that magma can convert some of the rocks nearby into, again, it changes that crystal composition and structure of the rocks into these rocks called metamorphic. And we'll be labeling some of these later. But for example, a rock like marble, it's a sedimentary rock called limestone, but when it's been recrystallized, it is marble. Again, and then sedimentary rocks, they're formed as either of any other kind of rock gets eroded by, water rushing over them, ice freezing and thawing, rocks break into pieces, and then they accumulate as layers or sediment, usually in a marine or an aquatic environment, sometimes on the land, but the rocks have eroded from the land and they wind up in the water in various layers. So the important thing is, of course, that the lower layers are older in time, and then typically layers on top of that are younger in time, unless they've been twisted later on by mountain building. And all of this then, it makes the one thing that rocks of all three types are a continuum. And it just depends on the conditions that they get exposed to how they move from one to the other. So again, primary igneous rocks were melted and cooled, but if they're heat and pressure, they can be changed into metamorphic rocks. Sedimentary rocks can change into metamorphic by heat and pressure. Igneous rocks could erode and then their particles reassemble as sedimentary rocks. Metamorphic rocks could erode and their particles reform as sedimentary rocks. So any type, once you could identify the specific rock you have and which rock group it belongs in, you can ascertain a history of how that rock came to be. And this is just another way of looking at that. It's called the rock cycle. So, and these rocks come from the words that they are implied are from, so igneous is from the Greek ig, from ignite, fire. Again, they think of them as they were solidified from molten material. Metamorphic are changed. Morph is the operative word there. They were changed by heat and or pressure. And sedimentary are sediments that were reassembled or precipitated. And these are some of the common rocks in these categories. Things that we're going to see when we actually look at some of the beach rocks. In our area, igneous rocks are things like basalt, and we might have some pumice in our area, not likely, but especially basalt, which is a rock that cooled above the surface very quickly, small crystals, or rocks that cooled below the surface, granite or gabbro in our part of the country. Sedimentary rocks that we will find on the beach, conglomerate, which is just an aggregation of smaller rocks or larger pieces, much like concrete is a conglomerate in a sense. Sandstone, which is hardened grains of sand. Shale, which is hardened clay size of particles. We don't have too much ash in our area. That implies direct volcano deposition. But we're very common with rocks that chemically came out of ocean material. Limestone is the big one, and dolomite that we will find on the beach here in our area. We actually do find coal because it's been washed off the ships as they come into the steel mills. We'll talk about that. And then metamorphic rocks that we find often on the beach in our area are gneiss and schist, which are rocks like granite or gabbro that have been squeezed, and so they have the layering characteristic. Or we can find quartzite or slate. Slate is shale that has been squeezed and heated, and marble, which is limestone that has been heated. Okay, so it's the important thing I want to say is that the kinds that we will find these various types of rocks along the beach, and it will tell us a little bit of the history of that particular rock. So we're going to be exploring that, as well as then how those rocks came to be on our beach in the first place. Because where the rocks were formed and the conditions that they were formed in are not necessarily the conditions that we find where we find these rocks. And that's what makes sort of things a little bit unique here. For example, we're going to be finding some igneous rocks like basalt here on the beach in Lake Michigan. But you might ask, well, igneous basalt cooled directly out of lava pouring at the surface. Well, we don't have any volcanoes near us. And that is true. You'd find basalt at the surface in Hawaii, but not here. However, we do find it because glaciers are going to be part of the reason that rocks have been transported to us. So these are the conditions of formation of rocks. But the rocks that we find on the beach and Lake Michigan, none of these conditions sort of applied to get them to us. They just wind up here from a third thing or a fourth thing we'll see, which is the action of larger geologic things in the Ice Age, the glaciers. But this tells us about the conditions of when those, of what it was like when those rocks formed. Hopefully that makes some sense. All right. So yes, it's very important. Most places you go, the Rocky Mountains, anywhere else, the rocks you find are formed where you find them because you're near the bedrock, which is by definition the solid rock that underlies, you know, any soil you might have. In our case, our bedrock is pretty far down below the surface, at least on the shore of Lake Michigan. So we find interesting rocks, but they're not native here. They're not as we would say, autochthonous means it's formed where you find it, native. But the rocks we find generally were formed in other conditions in other places. But if they wound up in our area, of course, as we're going to see, by the action of glaciers, which is the determining geologic feature immediately that makes the geography of our Chicago area.
So native, and the alloctonous is things that have traveled there. They've gone. Ali.
Auto is formed at its location. Alloctonous traveled there. Another term is erratics.
So it's open. In the back.
Okay, so in the Midwest, here is the location of bedrock, igneous rocks, and metamorphic rocks. So these are rocks pretty much at the surface in these areas. And I've separated the two igneous types out from rocks that formed that cooled below the surface and are now at the surface, or rocks that were poured out as lava at one point and cooled. And then metamorphic rocks, which again have been either of these kind that were squeezed. So if you can sort of note, and the main thing to take from these slides is that obviously we are located down here at the southern tip of Lake Michigan. None of these type of rocks is native to our area, at least at the surface. If you go down 5,000 feet into the center of North America, you will find these rocks. But at the surface in our area, they are not present. But they are present at the surface once you start getting from mid-Wisconsin north. And then throughout Canada here, the general term for that is, it's called the Canadian Shield. These are the basement or the basement rocks really of the North American continent. And they are the primary igneous and metamorphic rocks upon which North America and most of the continents sit. Sedimentary rocks sit on top of these as a general rule, you know, because continents, you know, rising up out of the tectonic, the lithosphere. So the general thing I'd like you to consider here is that as a category, everything up here as far as the bedrock at the surface is igneous or metamorphic. You know, different areas have different exposures. Whereas down where we are at, you don't have any primary surface exposures of igneous or metamorphic rock. I've ridden my bicycle across the United States and around a couple of the Great Lakes. 12 years ago, I rode around Lake Superior. It was a 3-week adventure. Partly I wanted to go to see where these rocks are at the surface. So the Canadian Shield bedrock along Lake Superior, here are some pictures. These are actually metamorphic rocks called gneiss. You can see by this banding. This is classic banding. This is not a layering. This is banding. And same with this. So these are the bedrock rocks that one might find in the Upper Peninsula of Michigan or the lower part of Ontario. That's my bicycle. That for those who've never traveled on a bike, living for 3 weeks, that's my home for 3 weeks. As I did 1,300 miles around Lake Superior that way. I circled from, I guess I went clockwise. I had ridden around Lake Michigan 30 years earlier. So I've circled these two of the Great Lakes by bicycle. Now the sedimentary exposures in the Midwest, basically there are some exposures on top in the Canadian Shield here of Hudson Bay. But as you can see, pretty much once you're south of middle Wisconsin and the UP Michigan, that's where sedimentary rocks are native. Again, in our case, they're 50 feet down, 100 feet down below the beach sand, but there are no metamorphic or igneous rocks as anything close to being bedrock near us. Our actual bedrock, you can see it in a few places in the area. The closest to us is, of course, the famous Thornton Quarry. It's a dolomite limestone. It's 400 million years old. It was formed at a time when the Midwest was a coral reef near the equator. And the reason it's close to the surface at Thornton is it was a coral reef, and after the glaciers left, it was very hard resistant to erosion. So there was only 20 or 30 feet of sediment on top. It was easy to get to it. And that's why there's a quarry to access the rock. Below where we sit right now, for me, Hammond, these same rocks are about 200 feet down through sand and silt and clay, etc. But it is the first bedrock that you would find in our area. So this is our bedrock, the sedimentary rock, limestone / dolomite. The dolomite is just a more magnesium-rich version of limestone. Interesting points here. The actual rock formation name is called the Niagara limestone because this is the same rock. There you go. This is our bedrock, and it's exposed on the western shore of Lake Michigan up through the Mackinac Straits and at Niagara Falls. This is the actual rock that forms Niagara Falls. Some of us may remember that in the late 60s, they actually turned off the American side of Niagara Falls here to do some cleanup, not pollution. They just wanted to clean up the natural broken rocks there because people felt it was detracting from the beauty of the falls, even though that's a natural situation of how waterfalls sort of work. But at any rate, that's where you can find pictures like this. It was actually turned off. But the rock that Niagara Falls, the water goes over, is the same exact rock as our bedrock. It was formed at the same time in the same conditions, and we will see that what those conditions were like a little later. So that is our bedrock, and it's important to mention that because it's exposed here on the entire western side of Lake Michigan and also at the upper part here, the Mackinac Straits. Okay, so that sort of sets up the basic rock geology of our area, the kinds of rocks that you'll find, where they're formed and how they're formed and where they're naturally found as they formed. But of course, in our area, in actually all of North America to central Indiana, Illinois, the most important geologic force that has shaped the land that you and I know are glaciers. Just a couple pictures of glaciers. This is in Alaska. I've had projects there way back in other careers I had, and this is a picture of flying into somewhere in Alaska. And you can see here's actually 1, 2, 3, 4. There's about 5 glaciers sort of meeting here, coming from these ice fields. And the picture to take, or the impression from this I'd like you to Yeah, it is. Glaciers are ice that moves. I mean, to me, that definitely looks like a structure that's moving. They're actually moving. The different glaciers here are moving at different rates. Glaciers can move up to 30, 40 feet a day, which is pretty fast for most geological conditions outside of a catastrophic thing such as a volcanic eruption or an earthquake. But otherwise, mountain building, erosion, things like that happen pretty slowly. So glaciers are the one geologic force that on a regular basis moves at a constant and relatively steady rate, even if you may not think 30 feet a day is a lot. This is the front of a glacier in Mount Rainier National Park. I was camping in this area. The reason I have this picture is to give a good impression of what a glacier looks like. It is not just a nice clear block of ice that you might see, in your freezer. It's dirty. It's filled with rocks and everything that the glacier has picked up in its movement from where it started. In the case here, these glaciers accumulating snow, they're going to pick up rocks and grind away rocks from this mountain range, and they're going to start carrying them with them. As you can see, that's rock material that gets sort of pushed up as the glacier is moving. So this is the front end of a glacier where it's melting, and these are all the rock material that was in that glacier. And of course, as the glacier melts, it just deposits everything in its that it was carrying. So that's the reason I'm showing this slide is glaciers they're filled with rock material. They're not just some nice clear, block of ice you can break off and put in your martini glass generally. Okay, so glaciers in their motion leave characteristic shapes on the landscape. So these upper little slides, so imagine a glacier is moving in this direction from areas up here where the conditions are such that snow is accumulating and not melting. So the snow gets compressed into ice, over tens of years and over centuries and thousands of years, hundreds of feet of ice can form. And eventually it starts to flow, whether it flows down from higher elevations, as in the case of Alaska here, higher mountains as it's flowing this way toward the ocean, or as we're going to see, if ice reaches a certain thickness, it's very plastic. It sort of has a flow of like silly putty when it's under hundreds or thousands of feet of ice. It's not like just a brittle block in your freezer as well. So it'll actually flow and it will squeeze out sort of like the blob, if you will. So it will move from the areas that snow was accumulating where it was cold until finally it reaches either a low elevation or a lower latitude where the weather is warm enough that the ice melts. And then everything that glacier has been transporting gets deposited at the front of the glacier. In the case of the glaciers in our area, when the climate warmed after the ice age, then the ice retreated or it melted back. In fact, it vanished. It went all the way, up to Canada and finally melted there. But everything that it carries, of course, it deposits. It doesn't carry the rocks back as the ice melts. And the general structure of material deposited by a glacier is called a moraine. And a moraine is just a mixture of everything from clay-sized particles to sand to silt, to pebbles, to cobbles, to boulders. Collectively, this is known as till, and the structure is called a moraine. So where the glaciers stopped, you have actually generally a large end moraine that could be hundreds of feet above the surrounding land, but you still have you have the till component in moraine everywhere that the glacier melted back. I lived for a number of years in the western suburbs while I worked at Argonne, and there you sit on a structure called the Valparaiso moraine, which in our area starts at about US 30 or so. But this is what primary glacial material looks like as till. There's the 10,000 years of topsoil that developed, but if you cut into it, you see this is just a mixture of sand and silt and clay and pebbles and boulders and cobbles. Okay, so that's what till is like. That's the primary material that our entire area was covered with when the glaciers finally left about 10,000 years ago. It's till, because we'll talk about how you get to sand, etc., in a minute. Here's our minute. One of the classic examples of a demo in geology is the old sediment jar. So if you have till, which is again a mixture of particles ranging from clay to silt to sand to pebbles, cobbles, and boulders, there's no way you could separate them out by trying to pick them out physically without water. So if you put a sample of till in a jar and you shake it up, what's going to happen? Well, the heavy material settles out quickly. Things like the rocks, the boulders, the pebbles, then the sand, then silt, and finally the clay. It might take weeks for the clay to settle out of this mixture. This is an important concept to keep in mind when we're going to talk about why do we have sand on the shore of the lake. You know, the misnomer is often that the glaciers brought the sand down. Well, the glaciers did, but they brought it in the form of the till. And it's the thousands of years that the lake interface has been there that it, in the motion of the waves, it washes away the lighter material like clay and silt to deeper water, leaving the sand and the pebbles in the areas of high energy where the wave front is. And then, of course, over time, wind blows the lighter sand up into the dunes. Okay, but what I want to get across is that glaciers leave us this mixture material called till, and it's later separation by wind primarily that give us the sand on the beach, the pebbles on the beach, or the silt and clay that are in the deeper water as you go offshore. You can find some of these in our things like in the Valparaiso Moraine. You can see rocks that are scratched like this. That confirms that we had glaciers here, because the only process in nature that we have found that does this is a glacier. As that rock was being scratched around in the ice, moving past other rocks in the blob of ice, so to speak, that's where you get scratches like that. And I have, I've collected a number of very nice rocks like that in the Valparaiso Moraine. You don't find these on the beach because the scratches get worn away in the normal wearing down along the beach energy. So all of that discussion of what a glacier does is in service to describe the kinds of glaciers we had here. So the picture of the glaciers I showed in Alaska, very nice, big, but very small compared to the kind of glaciers that we had. We had ice sheets. The only place on Earth that's equivalent to this today is, of course, Greenland and Antarctica. And over the last 500,000 years, several times the climate cooled enough that huge amounts of ice began to accumulate because snow for centuries was accumulating and not melting. Two major areas in North America. It's equivalent in Northern Europe, but obviously today we're just talking about our area. And the ice got up to maybe 15,000 feet, 3 miles thick, similar to what we have in Antarctica. So we can actually use Antarctica as an analog to what it was like here. We can look at conditions there now, and we can see rocks here and understand that a similar thing happened here 20,000 to about 15,000 years ago. The ice was very thick in central northern Canada, and it stretched down, you can see all the way down almost to the Ohio River Valley. There were several different waves of ice. The final one came and went to about central Indiana, Illinois. Anybody who has ever driven I-65, about when you leave Indianapolis and go to Martinsville, that's where the glacier ended. And I went to graduate school at Indiana University, Bloomington. By the time you're in Bloomington, the final glacier had not gotten there. Okay, but the ice in our area was about 3,000 feet thick. So again, the major ice sheet was up to 15,000. By us, it was about 3,000. So that's twice the height of the Sears Willis Tower, if you will. So you can imagine something like that advancing at 30 feet a day. It's going to do a lot of changing of the landscape. And again, the ice formed up here, so it's carrying rocks all the way from those areas. Eventually, the climate warmed, and of course, the ice started to melt back because it warms from the south. And then all the material that was carried in the ice sheet from areas north get deposited as the glacier retreats. There's various techniques we can use to see which directions the glacier came. Part of it is going to be the rocks that I'm going to talk about. But this is a generally accepted view of geology over the last million years or so in the Midwest. We had, these are lobes of glacier ice. Okay, so you can see at different points of time, some of the ice coming, climate warmed, climate cooled, more ice advanced, climate warmed, climate cooled. The final glacial episode that really determines the geography of our area is termed the Wisconsin episode, and that's what this pictures. So you can see the final glacier went to about just south of Indianapolis, about near Springfield, Illinois. Curiously, maybe some of you have been in the Wisconsin Dells, Galena. The last several glaciations went around. There's hard, resistant quartzite rock here in Wisconsin, very tough rock, and the glaciers sort of went around that. They did not plow through it. So this is called the unglaciated, or sometimes the driftless area, because there's no glacial drift. It's another term for the till deposited in this area. But clearly where we're at here in Chicago, we were well under several thousand feet of ice. So in general, this is what I want you to picture. We had an ice sheet here that reached its maximum extent about 18,000 years ago. Again, coming from much thicker ice deposits north of us in Canada. Then it started to melt back. And again, there's various names given all these things. As it melted back, the Great Lakes become exposed. The ice dug out the Great Lakes. They were already low areas. And so it dug out the deeper areas. The water, the ice melting, it filled the Great Lakes, and then subsequently thousands of years of precipitation filled them. Okay, I do that in another talk and give the whole history of how the lakes came to be. But that sets up the rocks that we find here on the lake. It's the glacial processes that brought the rocks from further north. So here's our next part of rock basics. How do we identify rocks, and how can you identify rocks? Fancy chemical techniques, but really, a geologist in the field can use just a few physical kinds of things and you get a good idea of what you have. Certainly you can visually look at a rock. What kind of color, what kind of texture, kind of shininess may it have? That's luster. What is the size of the grains in the rock? Are they large or small that you really can't see them with the naked eye? This is important for igneous rocks. If you have large crystals, that implies they were cooled below the surface when the rock was made, like granite, or if they were small, they cooled quickly at the surface like basalt. Just with your hand, you can tell how heavy is a rock. You know, most rocks are heavier than water, of course, but things that have a lot of iron in them are much heavier than things that might not. Hardness, in a geologist's term, hardness is the ability to scratch or be scratched. Diamond is the hardest substance in the universe. On this scale of Mohs, it's 10. It's a logarithmic scale. But for practical purposes in our area, the hardest rocks we'll find are quartz and feldspar, which means they're harder than glass. Most geologists will carry a piece of glass with us, and we'd help us to scratch the rocks. Whereas limestone, which is calcite, is softer than glass, so it won't scratch it. So this is something we can use when we look at rocks. Sedimentary rocks are typically soft, except the sandstone, which usually is quartz grains, so it is hard. But most metamorphic and igneous rocks are harder than glass. If you're looking for limestone and you have a little bit of hydrochloric acid in a little dropper bottle, it will fizz. That's how we can tell limestone in general. And again, we look for the crystals. Are they separated or are they interlocked? That implies, interlocked implies igneous. Separated implies sedimentary or later heat and pressure. And yes, okay. So yeah, let's look at some rocks that we would find on the beach. And I've broken some here to show you what I'm looking for as a geologist. So on the left, that is basalt. Typically has dark crystals. Again, for the purpose of our talk, it's more detailed to go into too much detail chemically what these are. But quartz, there's a lot more quartz in granite than in basalt. And the granite formed below the surface, So it has large crystals. You can see the various different crystals here interlocked, whereas the crystals of basalt, because it cooled quickly, are small and you can't see them. So this tells me that's likely basalt. Both of these would scratch glass. So these are the two major igneous rocks that we'd find on the beach, basalt or granite. Again, here's our little geology kit. Got to have magnifying glass, a little bit of acid, and our scratch plate. So what do you find on the beach? In general, the igneous rocks you find, they are going to be crystals. They will scratch glass. They're fairly hard. They're dark in color and they're not layered. Okay, granite is a little lighter in color, but it'll have a lot of dark crystals in it. Gabbro is just a darker version overall of granite, which has a lot of dark, large crystals. But basalt and rhyolite are small crystals, but the important point is they will scratch glass. The metamorphic rocks that we'll find, they're also generally dark. Their hardness is +or -5, but they are banded. You're not going to see banding or layers in igneous rocks. You see banding in metamorphic rocks. And the big ones to see are gneiss and schist, or quartzite, which is quartz crystals that have been squeezed. Rarely we'll see some greens. And the sedimentary rocks that we find on the beach, they're generally light in color. They're generally softer than glass, except for sandstone, which is, since it is ground up quartz particles, it will scratch glass. They are layered because they were deposited in a sequence, and they will have fossils. So the big ones are sandstone, limestone, and sometimes we have some beautiful agates. So here are some of the igneous rocks that we would find on the beach. And these are from the beach. The dark ones like this is basalt and rhyolite. These were lava that formed at the surface up in the Canadian Shield, and they were brought down to us, saying what this is a greenstone rock. The large crystals here are granite, or that picture isn't so good there. Granite type rocks, or closely related things such as syenite, etc. But in general, these are rocks that cooled below the surface. You can see their crystals of different composition, where these are rocks that cooled at the surface, but these are igneous rocks. So the implication is, of course, they came from the Canadian Shield. This is just a close-up of some of the granites. The granite will have this peppery texture because you have a mixture of things like quartz and micas and feldspars all blended together. Sometimes the crystals are small. Again, the volcanic igneous rocks, the crystals are too small to see generally, but we have things like basalt and rhyolite. Porphyry had a slightly different cooling type of situation. Sometimes you can see some crystals, but these imply volcanic origin. And occasionally, if the glacier lobe came from Copper Harbor, Michigan, you can see copper minerals in the rocks. Copper minerals typically are green. You can find sometimes native copper on the beach. I have not found native copper yet on the beach in Lake Michigan, but there are reports of it. There are reports of diamonds being found on the beach, as well as small amounts of gold, because there are diamond and gold deposits in Ontario. But these would be extremely rare to find. You'd be very lucky. Okay, the metamorphic rocks that you would find, they look like igneous. They have similar hardness, but here's the difference. You see the crystals there, that's lined up in bands. Or this, that's lined up in bands. And you do not see, and the banding there, you do not see that in igneous rocks. These are the same minerals as in granite, but this implies this rock has been squeezed, or the layer that the area this came from was squeezed mountain building before the eroded piece, of course, worked its way down to us. And then over thousands of years on the shore has been eroded into the round rocks. That's why all the rocks we sort of see at the beach are fairly rounded, because they've been later on eroded by the beach action. Okay, but metamorphic banding. So this looks a lot like granite. It's the same minerals, but that banding shows me that that rock had been reheated after it was originally formed and before it was brought down to us. Okay, the sedimentary rocks, sandstones. Basically, it looks like hardened sand. Okay, grains of sand, it'll scratch glass, has a sort of a rough appearance, and this is layering. This is not banding now, this is layering because of course the sand was deposited in layers, one layer of sand, then another layer, then another at the bottom of an ocean before it hardened into sandstone. Conglomerate is sandstone with just larger particles, large enough to have cobbles or pebbles. And it's sort of a natural form of concrete in a sense. You know, concrete is made with rocks of various size that are bound together with a lime mixture to harden. And essentially, natural conglomerate is much like a concrete kind of mix, but this is very common along our beach. Rocks, sedimentary rocks that form by evaporation or precipitation, that's the family of limestones and dolomites. They formed at the bottom of an ocean, chemically at the bottom of a saltwater ocean, which of course is nothing like what we have today. So now we're going to talk about time, a couple more things. And the other really nice sedimentary rocks are agates. Agates are quartz that formed in layers, and quartz is very hard. These will scratch glass, and they have beautiful layering to them. Lake Superior agate is very popular. You don't find it too much on our shore. You got to be further north, but you can find agates like this. This is sort of pure quartz, but it's microcrystalline quartz in the general category of something we call chert or jasper. All right, so back to now. Next, we talked about where they're formed. Well, let's talk about when these rocks were formed. Most of those igneous and sedimentary rocks, they're exposed in the Canadian Shield. They're the oldest rocks in North America and some of the oldest rocks in the world. They could be billions of years old. The sedimentary rocks can be hundreds of millions of years old, but they're on top of it, and they'll have the layers of strata. And this, the general category for this, of course, in geology is oldest on the bottom, youngest layers on the top, unless you had mountain building to switch things around, which we haven't had in the Midwest for hundreds of millions of years. So again, we'll go to the Grand Canyon, for example. So there I am, 3,000 feet into the canyon. So this layer of rock is older than that layer of rock. It's a general rule. They're the pages in our book. And we, of course, organize things in something, the geologic time scale, from oldest to youngest. Geologists kind of name things just like any scientist. So in our area, our bedrock is this period of time, the Silurian. It's 400 million years old. That's our local bedrock. And all those other rocks that we're finding are way before that, maybe 2 billion years old, because that gets exposed at the Canadian Shield. And then we basically have nothing else here because of the glaciers, except in some rare cases. And at the end of the talk here, there's a lot of talk in science now that we've actually entered a geologic time frame, not just, so this is sideways instead of vertical, but the Anthropocene. In other words, the era of human effects. And we'll see, you can find rocks like that on the beach. All right. And 1950 is sort of when the Anthropocene is generally thought to have started. Nuclear weapons, the amount of pollution that society makes, the carbon increase, all that sort of date to really around 1950. So that's about the Anthropocene. Okay, so the rocks in the upper Midwest. Remember from my earlier slides, the Canadian Shield here are generally igneous and metamorphic, and they are old. 1 billion to 2 or 3 billion years old. That's when they were formed. Whereas the rocks, our bedrock rocks, are formed 300, 400 million years ago. And this is just another way of looking at that, the time periods. This is sort of a cross section across Lake Michigan, and you can see these are all sedimentary rocks, all those layers. Here is the rock we have exposed, like right up. We would be right here. There's our Niagaran rocks that come out again here at Niagara Falls. So Our bedrock formed when the earth looked like this. Chicago would be down here, and we were actually underwater, a shallow marine ocean at the equator. That's when that Niagaran dolomite limestone formed. Chicago was right about here 400 million years ago in the Silurian. So what kind of animals would be living in there? Well, that's the fossils we find in those kind of rocks. And these are examples. We have things like trilobites, many kinds of corals, animals called crinoids, which are related to starfish, but they lived on a stalk. These are very common fossils on the beach. You can find fossils of shelled animals like brachiopods and clams. So this is our native bedrock. Here, let's talk about then the fossils we'll find out. My favorite things are crinoid stems. I have a necklace made out of them. Many people call them Indian beads. They really have nothing to do with Native Americans. We find coral. Petoskey stone, which is the state rock of Michigan, is a coral. And occasionally we can find some brachiopods, or super rare, you might actually find something that the glaciers actually was living with the glaciers. And I have one specimen in my collection. And then the other kind of life is this new human anthropomorphic in the Anthropocene. And these are some of the interesting things we'll find. So let's look at them. So in our bedrock, or the bedrock around Lake Michigan, because remember, this type of rock is exposed all the way up to the Mackinac Straits. You can have these kind of rocks that were eroded as the glaciers came down. Coral is one big category. This is a living horn coral, what it looked like back then. These are the fossil corals. It's, again, you're seeing sort of this hard part of the animal. Sometimes you'll see honeycomb shapes because, of course, you can see how they lived here, the corallites. So these are all corals, very common things. Sometimes you see a rock with lots of little holes in it on the beach there, it's most likely a coral. Again, here's another coral that I found on the beach. You can see the little animal grew this way, so it would grow up and the coral would increase in size. Favosites is a very common coral. Petoskey stone is actually another type of that coral with the hexagonal structure. Occasionally you find them on our shore. They're usually small. You need to go up on the western shore of Lake Michigan near Petoskey. That's where you find more of them, because that's where they've eroded right out of the rock. But people polish them up or just put them in the water and you get this beautiful shape. You sort of find them on our beach. They might be like this until you've put some water on them. But Petoskey is a coral. It's specifically a hexagon area. And again, it's exposed in the surface nearer to the Mackinac Bridge. But we do find it down here because, of course, that layer of ice came from that direction. By far, my favorite thing are to look for these little beads. It's the stem of this crinoid animal. Basically, we do not find the head. This is very fragile, and it got destroyed in a lot of the fossilization process or the later erosion. But the stems are pretty tough. And so they erode out of the sedimentary rocks and they wash out, and you'll see them on the beach pretty easily. Usually every time I go to the beach, I don't leave until at least I have one. I found at least one crinoid stem, whether it's a single stem or I've got a little bit of a section, and I actually have enough. I've made a necklace out of them. So that's my favorite rock to find. Again, they're not Indian beads, but people often call them that. But they are stems of an animal. And sometimes you'll find the limestone itself that has crinoids embedded. This is just an earlier stage. This rock hasn't had enough time to erode in the beach to erode out the actual segments. You can see the segments are in there. See there? Okay, sometimes you can find fossils in the sandstone. Here's a piece of sandstone that's layered. So this layer is a little older than this part, but you'll find vertical marks through there. These are worm tracks. 400 million years ago, this was sand at the edge of the ocean. It hardened, and many of us, if we've been to an ocean today, there are worms that live on the interface of the water. We don't have any freshwater worms like that today here in our area, but saltwater worms. And so this shows that there was a worm trail boring through the sand 400 million years ago. Then that sand later hardened into rock. Of course, the worms don't preserve well. They have no hard parts, but the trail they leave sometimes does. So these are worm tracks in sandstone that was originally formed hundreds of millions of years ago, a little bit north of us, and brought down by the glaciers. Now, I found a couple small brachiopod shells in the sand. These are not common, and one part of what I think is a trilobite. Trilobites are common fossils, but not really in our beach rocks. I think the segments break off too easily. I believe that is a trilobite. You can find also other colonial animals that are not corals, but they're sponges, and these are common. So this is sort of the layering of the animal as it grew in these various levels. A stromatoporoid is similar to a coral kind of animal, enough for our purposes today, but it was a colonial animal living in that 400 million year old ocean that covered the Midwest when the Midwest was at the equator and formed our bedrock. And again, our Niagara dolomite, the reason we find it at the beach is because it's exposed on the western side of Lake Michigan. Door County has many deposits, and so the glaciers have brought that rock down to us. Sometimes you can see tar in it. You'll see tar if you actually go to the Thornton Quarry. It seeps right into the quarry. There's natural oil here. And the last bit of very interesting, very rare, but I found back when I worked at the national park, I found a baby tooth of an Ice Age mammal. I don't know what kind, but in the ice. So this is from the Ice Age. It was deposited when the glaciers were here and survived all that time as the lake was washing in and out the sand. You see, it's not real big. It's about 1.5 inches, but that is the rarest thing I found as far as fossil animals on the beach. Other interesting things you might find on the beach are fulgurites. Lightning hits the beach, it melts the sand into something called a fulgurite. And these are not that rare. It's rare to find nice long ones, but I think we've all seen lightning hit the beach. Well, that tremendous heat will melt the sand. And if you're lucky, you can find, it usually has this dendritic appearance because the lightning, as it melted through the sand, has that. All right, so the last little things that we see are, again, there's a lot of controversy in science. Should we call everything since 1950 the Anthropocene because we're affecting the world in such important ways as a new geologic time? Well, things that we find on the beach that are modern, again, there's no coal found in the area here that should come from the north, but I find coal pieces because, of course, they're carried on the ships to the steel mill and they wash off, as well as slag from the steel mill. This has a bubbly appearance of, you might think it would be pumice, which is a geologic rock formed as bubbling out of a volcano, but it's not pumice, it's steel mill slag. I've also found a lot of bones of freshly cut somebody's dinner that somehow is washed into the beach and over years has eroded away. So that's a garbage bone. You can find broken asphalt that's worn away. This is part of an old pier. It's concrete. I thought it was an interesting fossil at first. I thought that looks like a plant, but then I realized, no, the geology doesn't make sense. And I looked and it's rust with holes in it where screws were. So that was a broken up pier that probably has been washing around the shore for 80 or 90 years. So that implies human. Occasionally you see bricks worn out, or I've seen broken clay pots. And of course, a lot of people collect beach glass. Doesn't take too long for a broken bottle because sand is hard. Remember back when we talked about rock hardness, most sand is quartz grains, hardness of 7, glass is a hardness of 5. Rolling around in the beach sand will erode glass. This is not to have you break your bottles on the beach so we can cut your foot, but inevitably, of course, there are bottles that have been on the beach. And the last thing that the Anthropocene shows is, of course, unfortunately, the tiger mussels, the zebra mussels, and the quagga mussels really zebra mussels, that tiger, they're tiger striped. You find them now too, because of course they're recent arrivals on our scene, but you can find them on the beach as well. Still the fresh shells. So the final thing I want to leave is the rocks that we find on the beach along the Lake Michigan, tell us a story of time, of when those rocks were formed, of the kind of environments that they were formed in, magma, lava, mountain building, or in our bedrock case, bottom of an ocean, and where they were formed. Igneous and metamorphic rocks formed far north of us, and then sedimentary rocks formed everywhere from our area or north of us, all of them brought down, mixed together on the beach on Lake Michigan because of glaciers. So again, we have time, rocks from 2 billion years ago to 400 million years ago, and all this was transported down in the last several thousands of years. And then so the environments, again, the igneous and metamorphic rocks that make up North America, which are characteristic of volcanoes and mountain building and squeezing, or marine rocks, sandstone, limestone from long ago, but not as long ago as that, rocks. And then the recent ice age rocks, which are very rare to find. My mammoth was the only thing I can show. And again, place. North of us, all of these things came and are brought to us. So next time you're walking along the beach, think of the stories that the rocks can tell you about what has happened here all the time ago. So there we go. I found that on the internet as an agate. And there you go. I'm going to stop the share so we can see me in person, I guess. And I'm willing to take questions. Okay, Jane, unmute yourself.
Sorry, just turning off. Oh, I did. All right, so I've got a couple questions for you. Like, I love this. This is a great talk. And I'm teaching earth science. Not teaching it this year, but I'll probably be teaching it again next year. And I teach high school kids locally at St. Francis de Sales, which is over on the east side of Chicago. And I would love to take the kids to the beach to go rock collecting, but I don't want to do something that's illegal or teach them things that are not safe. So like, I know, like I've gone hiking all along the shorelines of Lake Michigan and like the Illinois Beach State Park. There's tons and tons of rocks around there, but is that legal to be like collecting rocks out of the lake? I don't want to like be setting bad examples for my students.
Okay, so that's a good question, and Mike should turn off the recording part now. But so I do a talk in the fall for the Indiana Dunes, part of their outdoor festival, and I lead this talk and it's a national park now, and the state park, all these rules, you're not to collect anything. In the case of the dunes, the park sort of does turn an eye the other way for all of us that have beachcombed for years. It's not